I am Kulwinder S, Professor of Medicine and Pediatrics at the Medical College of Wisconsin in Milwaukee. Today I will be commenting on one of our review articles on repairing esophageal injuries with tissue engineering that is in press in the journal Gastrointestinal Endoscopy. Using principles of regenerative medicine, it is now possible to regenerate tissue and even regrow a whole organ. These principles are based on populating pluripotent cells on extracellular matrix or growing an organ in a bioreactor and then transplanting the organ into the host animal or a human being. Since majority of these studies have been done as a proof of principle in animals, initial results on trying these techniques in human beings have been mixed but overall promising. In this review, we discuss the approaches used to repair esophageal injuries using some of these techniques. Now, why esophagus? Esophagus can be injured in many ways, and this can lead to significant morbidity and even mortality. We defined esophageal injuries as three types. One is partial thickness defects, when the lining or the mucosa of the esophagus is stripped, as we do for people with superficial esophageal cancer or dysplasia. Endoscopic mucosal resection or dissection, when it involves more than 2/3 of the circumference of the esophagus, can lead to stricture formation, offsetting some of the benefits of curative resection. These are partial thickness defects. As compared to full thickness defects that can be focal or patchy, as seen with perforation that can lead to fistulas and leaks. The biggest defect, however, is when people undergo esophagectomy and almost the whole esophagus has been removed, and these defects are long segment circumferential full thickness defects, and over here the patients have to undergo gastric pull-up or colon interpositions with long-term morbidity and poor quality of life. Our basic aim for partial thickness or focal full thickness defects like perforation is to preserve the organ rather than subject these patients to esophagectomy. And on the other hand, our basic goal for people who have to go on esophagectomy for cancer or atresia is to regrow the organ to reestablish luminal and functional continuity rather than artificially make conduits. So let's start off with partial thickness defects. When the mucosa is stripped, the immediate reaction of the body is to induce fibrosis because epithelialization is a slow process. So in some way, if we can induce epithelialization quickly before fibrosis sets in, we can prevent stricture formation. In animal studies, this has been done by injecting pluripotent cells like those derived from adipose tissue into the resection site so as to hasten epithelialization and restore mucosal barrier. In another way, this can be achieved by initially taking some squamous cells from the buccal mucosa of the animal, culturing them in vitro into cell sheets about a week or two before the endoscopic resection, and then applying the cell sheets to the resected site to immediately restore mucosal barrier. And these approaches have, in animal studies, shown to be very successful in preventing stricture. A group from Japan used the cell sheath technology in human beings and were successful in preventing stricture formation. So basically what they did is that they cultured the autologous buccal mucosal cells of these patients about 10 days prior to the mucosal resection into cell sheets, and on the day of the mucosal resection, endoscopically after the resection, they transplanted these cell sheets to allow the epithelium to grow fast and prevent fibrosis. Another group from the United States did pan-mucosal stripping, extensive stripping of almost all the mucosa circumferentially from the esophagus in patients with long segment Barrett's with high-grade dysplasia, and achieved the same mucosal or barrier coverage with extracellular matrix rather than using buccal cell sheets, and achieved success in preventing stricture formation. Focal defects, which are full thickness like perforations, have been successfully treated endoscopically with clipping, suturing, putting stents in, and even with endoscopic vacuum therapy. However, patients with large defects or those who have failed endotherapy have to be referred for esophagectomy with associated morbidity and mortality. A group has also from the United States restored or preserved the organ by patching up these large defects with extracellular matrix and regrew those segments of the esophagus that were damaged in this process and therefore preserve the organ. The biggest challenge, however, comes when patients have to have their esophagus removed for cancer or long segment atresia. So over here, preserving the organ is not an issue because the organ has to be removed because of the primary disease. So regrowing the organ over here would be ideal as compared to doing gastric pull-ups and colon interposition. Animal studies have shown that this is possible. For example, a group from Pittsburgh resected 5 centimeter long segments of a dog's esophagus and applied the principles of regenerative medicine by implanting extracellular matrix with autologous pluripotent muscle cells, and were successful in regrowing the organ, which they later on confirmed histologically to show normal 5 layers of the esophageal wall. This approach has not been tried in human beings until recently. Our group recently published a paper in The Lancet where we were successful in regrowing a 5 centimeter long segment of the esophagus by using donated human skin as the extracellular matrix that was held in place with expandable esophageal stents, and pluripotent cells like stem cells were attracted to the site by spraying that area with platelet-rich plasma that have factors that attract the stem cells to the site. Extracellular matrix is a unique tissue that can also by itself induce organogenesis. It is decellularized tissue and therefore it has got altered immunogenicity and can be used either from pig small intestine or urinary bladder, or it can be used from allogenic tissue like donated human skin. And the matrix has preserved vascular network. It produces substances that attract stem cells, and the stem cells then differentiate into tissue-specific phenotypic cells leading to organogenesis. So, in summary, esophageal defects, whether they are partial thickness, full thickness focal, like perforations and leaks, or total loss of the organ, like after esophagectomy, using the principles of regenerative medicine, we have promising results in repairing these defects, and these have been now validated in animal studies. They are not yet ready for prime time. They are extremely demanding in terms of expertise, expense, and regulations, and initial results are promising. Thank you.